Okay, everybody. We're only a minute late. We'll give our previous lecturer a hard time later. Nice to see you all. I'm glad that not all of you guys did the thing where like your midterm scores come out and you punish the instructor by not going to class. It's nice to see your smiling faces. So in case you haven't seen, your midterm scores, I believe, are visible on the Canvas site. Is that right? Oh, just kidding. Well, they're top secret and they're entered in the Canvas website. We have an unfortunate situation, which is I actually hand graded all your midterms, and then I handed them off to our TAs for just typing in the numbers, because that's where I draw the line. And then unfortunately, Leticia got sick, so currently all of your midterms are kind of trapped in her office until she gets better. But eventually we will hand back the papers, and in the meantime, you'll see your scores. Don't panic. My goal is to give people high grades in this course. The grades for this midterm were kind of all over the place, would be the phrase I would use, which makes it a little bit tricky, but we'll find a way to make sure that everybody does okay for their final grade for this course. And I might try to think if there's some way that you can do like one of these like midterm corrections kind of thing to get a few points back, if that's valuable. I haven't thought about the right mechanism because I know there's a lot of policies about adding late homeworks to courses and I don't want to add to your stress. But I do want to make sure that you guys actually digest the content of this course. And while it was a long exam, what kind of scared me a little bit is that there were some pretty basic calculations on there that some folks got wrong. And I do want to just have you practice that a little bit. And so we'll come up with some mechanism to at least encourage you to do that kind of thing. In my experience, oftentimes what happens is that the final exam grades are a lot higher than the midterm ones anyway, because we scare you into studying, which is fine. Recall that the midterm's actually not worth a ton in this course. In any event, beyond that, I believe you have a homework due, and then you're almost done with this class. I think you have like, what, one more homework and an exam, and that's about it. So you're almost done with the torture, and then we set you free for Christmas breaks, winter break. Any questions, comments, concerns? Okay. Yeah, unfortunately for you, there were some people that kind of made it difficult for me to scale the midterm exam grade, just like shift it upward, because a few of you actually really did well. I'm gonna have to make it harder next time, which I'm sure you all love to hear. In any event, so today we are going to continue our discussion of the conjugate gradient algorithm. I think this is one of these fun ways to kind of bring together several topics that we've heard in this course. In particular, remember that we started by talking about linear solvers, but the kind of algorithms that we covered, things like Cholesky factorization, LU, and Gaussian elimination, really looked kind of like your undergrad algorithms class in some sense. Like they were very much kind of step by step. They terminated in some number of iterations, and then up to numerical precision, they really do give you exactly the solution to your linear system. And then, after we concluded our discussion of numerical linear algebra, we moved into this much more kind of fuzzy world of optimization and root finding, where now we don't expect to be able to solve our problems exactly anymore. The best that we can do is derive iterative algorithms that essentially take some guess of the solution of our problem and make it better and better and better and better and better, but we can never quite get there. And now, in this little segment of this course, we kind of do a weird thing, which was we put on our optimization hat, but we particularly study the linear algebra problem from the perspective of numerical optimization. And the basic point here is that they should make that, if just like a half a foot lower would be nice. Okay, if I want to solve ax equals b, and moreover I have that a is symmetric and positive definite, then that is exactly the same as minimizing over x the following objective function, 1/2 x transpose ax minus x transpose b. Hopefully we all, at this point, kind of understand the connection between these two, right? Namely, if you take the derivative of the problem on the right, you end up with the problem on the left when you set it to 0. And what that allows us to do is to take any of our optimization algorithms and directly apply it to solving linear systems of equations, at least with this assumption on A. Notice, by the way, that if we needed to relax that assumption on A, as somebody pointed out in our previous lecture, we also could have applied it to this objective function here. But one thing that we saw in our previous lecture is that the convergence rate of the algorithms we cover tends to do with the conditioning of the matrix of our linear system. And as you know, the matrix of this thing is going to be A transpose A, whose condition number is roughly the square of A. So if we can avoid that, then we should. Right? So for now, if we know that A is symmetric positive definite, then this is the optimization problem we should consider, right? And in our previous lecture, we made a few observations about this particular problem, which make it obviously a lot nicer than just a generic optimization problem. Now, by the way, let's say that I want to use this kind of idea for solving linear system. Would Newton's method make any sense? This relates to an exam problem, incidentally. I mean, what is Newton's method going to do? It's basically going to call a linear solver to solve ax equals b. So Newton's method probably doesn't make sense. However, a gradient descent probably does, right? It's easy enough to compute the gradient of this objective function and to decrease it step by step and to get a better approximation of x star, which is our minimizer. Yeah? Okay. Right, so that's going to lead us to this beautiful algorithm, which if I quit talking so much, we will get to today, which is called the conjugate gradient algorithm. And it's sort of the best of both worlds in some sense. And it's also our first example of an accelerated gradient descent procedure, where what we notice is the following. We can do gradient descent on this particular problem, and actually we can do a little bit better by improving our line search procedure. I'll recall that in a second. But we can observe that gradient descent applied to this objective function still doesn't have to converge in some finite number of steps. That is, it successively makes better approximations of the minimizer, but it never quite gets there. And so like if you wanted the best possible solution of ax equals b, there's some crossover point where you might as well have called Gaussian elimination, right? So think about it this way. This is, by the way, just a little bit of review, because I want you guys to see the point of using these kinds of algorithms. If we call this thing our objective function like f of x, then the gradient of f is going to be, I guess, ax minus b. So for a generic, that was supposed to be an f, kind of got away from me. Looks like a 7. So think about like one iteration of gradient descent. Like essentially, let's say that A is just some generic n by n matrix. What is the cost in terms of n of a single iteration of gradient descent? Any ideas? Bueller? Yes. N squared, that's exactly right. Because I have to evaluate this expression, and just computing the product, a times x, takes n squared time. Notice that's kind of obvious in a sense, because like at the very least I have to look at every element in A, and that there's n squared of those. So what does that mean? Well, so a single iteration of gradient descent, unless I know a little more structure about A, which I often do, takes n squared time. So after n iterations of gradient descent, I might as well have called Gaussian elimination on this problem, right? And notice that like we haven't actually proven that after n iterations of gradient descent, we really get a good solution of this optimization problem. So there really is a bit of a crossover point here that's a bit hard to characterize. Does that make sense? And so the conjugate gradient algorithm from like 1,000 miles away tries to ask the question of, can I make a gradient descent-like procedure that still is guaranteed to outperform, or at least is guaranteed to do no worse than Gaussian elimination? Namely, after n steps of that procedure, I'm guaranteed to have the optimal solution to my problem. We haven't proven that yet, but that's where we're going, to give a spoiler alert. Does that make sense? And so like that's what we're aiming for. And doing that is this really subtle and tricky calculation. I mean, every year when I teach this stuff, I intend to dig into the history of this algorithm because it is a little bit magic, and then every year I forget. So maybe one of you guys can look at the Wikipedia page and let me know. So anyway, as usual, I've put on the board all the things I wanted to say in my slides, and now I'm going to page through my slides because I forgot they were there. But essentially, Gaussian elimination is cubic time. We want some method that looks like gradient descent, but is never outperformed by Gaussian elimination, at least asymptotically speaking. And in particular, where algorithms like conjugate gradient really shine are when your matrices are easy to imply but hard to invert, right? So sometimes we know that an operation is linear, but actually extracting the individual elements of the matrix is quite expensive. But we can write some piece of code that like takes in an x and outputs an a times x, right? Like when your matrices are structured, for example, in differential equations, this comes up a lot. Then essentially the kind of beautiful thing about conjugate gradient method is it never actually needs access to individual elements of A. It only ever needs access to a piece of code that inputs an x and outputs A times x. And that's not always the same thing as just storing A as a matrix. You could write like a piece of code, for example, that like knows that A has some particular structure and just computes it directly. So as a simple example of that, one matrix that shows up in differential equations. By the way, this is all review from our previous lecture, but I know that this stuff is abstract and weird, so repeating it a few times is okay. a very typical matrix that we see in this world is this tridiagonal thing, which is like 2's and -1's. Right? This is kind of like a second derivative matrix. We talked about this last time. And there are two ways that you could imagine implementing a product times a times x, right? One of them would be to store all of this stuff, right? The other one would be to take 2 times the elements of x and then subtract off their neighbors, just like using a for loop. And those are exactly the same from perspective of matrix vector product, right? And in that case, I don't have to store anything. I just have to store a -1, and a 2. That makes sense? And so there's a lot of matrices out there in the universe that are essentially so structured and well-behaved that I don't even have to store them. I just know how to derive the matrices from the problem, and then I can apply them directly. Okay? And in fact, by the way, the JAX programming language has some really cool functionality for doing this. So you like write a piece of code and it can even like apply the transpose and some other things kind of implicitly, which is really cool. I encourage you guys to take a look. Okay, so anyway, now you get our point. We're going to try and come up with an iterative algorithm, but we never want to be outdone by Gaussian elimination. That's our high-level goal. And in particular, in today's lecture, just like last time, we're going to assume that our matrices are square, symmetric, and positive definite. And at the very end of lecture, if I stop talking so much, we'll talk about some ways to overcome these assumptions. And there are quite a few. This is a whole, like you could easily cover an entire course on iterative linear solvers, and we're just scraping the surface here. Okay. So we're going to study this optimization problem. I'm going to zip through because this is all review from last time, but I know that it's review of stuff with a lot of indices and notation, which is why I think it's worth repeating rather than just assuming you can page it back up into your memory. The very first algorithm that we derived last time was gradient descent, but with a bit of a twist, right? So if you recall, remember the gradient of our problem is ax minus b, right? So here, d is our search direction, so it's minus the gradient. Remember, gradient descent moves along minus the gradient direction. And we said, well, if we take our objective function and we restrict it to straight lines. So for example, if I'm standing at x and I look in the d direction, right? It's like I'm skiing. Then like this is a quadratic function of x, and now I'm just along a single line. So this thing is just a parabola, and in particular, I can extract a formula for alpha, which is the absolute minimum of this function along the line through x in the d direction, right? And this is just a question of minimizing a quadratic function in one variable. That's all. Hopefully this makes sense. We kind of remember we're paging. The thing is I'm putting all these formulas up because we're going to need them all today. It's going to get real ugly real fast, so get excited. So this is our basic gradient descent algorithm. Notice, by the way, this is way easier to code than Gaussian elimination. It's 3 lines of code, and it is guaranteed, at least asymptotically, to reach the minimizer of our problem. But one thing we saw is it kind of looks like the convergence rate of this problem ends up looking like the condition number of our matrix, which isn't so great. And so what we ask is, can we do better? Like in particular, can we come up with an iterative algorithm that we might stop early, but if we don't and we run it for n iterations, it's going to stop anyway. Namely, at that point, we're competitive with Gaussian elimination, and we really will find the solution of our problem. And moreover, if we kind of look at the iterates of gradient descent, we see that they often kind of zigzag. Right? We saw these diagrams last time that kind of look like this. And so there's somehow a lot of work that, like, if only we could have guessed that our problem really needed to move along that line, we would have done a lot better. But sadly, that's just not the gradient direction that we got. And so that's the kind of thing we're going to try and address today. So we're almost caught up with our previous lecture, I promise. To give just a little more color, essentially what we did in our last lecture is kind of a sneaky change of variables. We said, oh, well, if we know that A is positive definite, then even if we don't choose to actually calculate the Cholesky factorization, we do know that it exists. Right? So we can use it in our mathematical derivation of these algorithms as long as we kind of eliminate it later. And that turns out to be a useful convenience. And so the basic idea here is that we take our original objective function f, that's this guy, and what we proved in the last lecture is that we can understand f as the formula above. So x star is the solution of our linear system. And essentially, what we showed is that the quadratic form, if we shift it from centered about 0 to centered about x star, we get a linear term. And what that allows us to do is to write f in this kind of interesting form at the bottom of the slide. Right? So essentially, the way that we can think about this objective function here is that it's kind of minimizing, it's trying to calculate the distance between x and the optimal solution to our problem, but in this weird coordinate system that's determined by L. Now, This is a kind of like fun theoretical fact. Is this useful for algorithms? Well, it's not so obvious because we don't actually have access to L. If we did, then we might as well just do triangular solves to solve our system. But at least theoretically, we kind of know what this optimization problem is doing. Really, it's just some notion of distance to the optimal solution in a weird coordinate system L. Okay? Now, what we proved in our last lecture, I rushed through a bit, but I'll let you guys review the proof because it's actually quite straightforward, is the following little fact, which says, okay, we define two vectors v and w to be A conjugate if v transpose A w is equal to 0. And remember what that means. I think the thing to keep in mind every time you see this is that v transpose A w is the same as v transpose L transpose w, like that. So in other words, it's the dot product between LV, or L transpose V, rather, and L transpose W, right? So this is just like a dot product in some rotated space, okay? And in fact, by the way, we're going to use notation today. We're going to call this the inner product of V and W with respect to A. If you take a Riemannian geometry class, you'll do a lot of this kind of thing, okay? So the basic idea here is the corollary that we proved in our last lecture, admittedly in a bit of a rush fashion, but it's a straightforward one, is that if we have a set of A conjugate directions, and I do line search along one of those directions, and then the next direction, and then the next one. Notice this is kind of weird. Like gradient descent, we typically choose our search direction based on where we are. But here I'm just saying, like, I just come up with a list of search directions a priori. I totally ignore the gradient of my problem, right? This thing is saying, if I come up with a list of conjugate directions, then after I do line search along each one of these things, my linear system is solved. Notice that that's kind of a hint toward what we were looking for in the conjugate gradient algorithm, right? If only I can identify efficiently a set of conjugate directions, then if I just do line search along one and the next and the next and the next and the next, then after n steps, my algorithm converges with a capital C. Like literally, it reaches the minimum of my problem. I can't do better. And I've stayed competitive with Gaussian elimination so long as the amount of time it takes to compute the V's is not too high. Right? Like if it took quartic time to compute all these V's, then I already lost. Does that make sense? Right. Everybody with our story so far? I think that's like roughly where we left off last time. It's okay if you're not. Ask now because we're about to like dive into weird indices. It's going to get ugly. Okay. So that's our story so far. I mean, and by the way, the reason that this is true, if you kind of look back at the proof, is that what we show is that every time you do one of these line search operations, you're kind of adding another V into your subspace of directions that you've looked at so far. And essentially you can show that each iterate kind of remains optimal. Like you don't, like by line searching along this direction, I didn't lose some of the progress I made along one of the other ones. That's essentially what's going on. And that's going to become the really, really important fact we're going to use today if I don't screw it up, because I'm really afraid of the proof of conjugate gradient. You can see I wrote my handwritten notes and I've got printed out pages from the textbook, and I'm hoping between one of those two we'll manage to get it together. Okay, this is one of the more ugly things we do in this course, but it's a beautiful algorithm at the end of the day, so it's worth it, I promise. Okay, so these are our high-level ideas so far, is that the direction of steepest descent, like the gradient of our problem, might not be in some sense the fastest descent, right? From that previous slide, like if rather than just doing gradient descent, I kind of had some foresight and I did like some procedure that gave me conjugate directions instead, then eventually that strategy will win out, kind of guaranteed. And moreover, we kind of have to navigate the difference between two different dot products, right? I mean, so far in this course, we've mostly done the sort of Euclidean dot product, like v dot w, but now we've introduced a new guy into the picture, like v transpose AW, which is really just a dot product in some rotated space. Okay? And so I think the way to understand conjugate gradients is like, I'd really love to do gradient descent in this kind of like mirror world where everything is multiplied by L's, but I don't really have access to that. And so what we're going to do is kind of derive a gradient descent looking algorithm in that rotated space, and then basically just put parentheses everywhere in a clever way, where we're going to notice that like every time there's an L transpose right next to it, and that actually we were just multiplying by A the whole time. That's kind of what goes on in this method. I'm going to keep repeating these high-level stories because I think it's so easy to get lost in indices in this algorithm, and I hate that there's this document out there called CG without the agonizing pain, which makes you people feel like it's painful, and it's not. This is a really simple algorithm. It's like based on really clever ideas, absolutely, but the actual derivation is pretty natural once you see the kind of basic observations that some folks have made. Yes?
When you say rotated, you mean more like rotate and stretch?
Oh, that's right. Sorry, I'm using the word rotate in some generic fashion. I really mean like up to some linear transformation. That's absolutely right. In fact, if L were a rotation, notice that LL transpose would be identity. So you're right. This is bad choice of words. Okay. So if you believe my story so far, then hopefully you agree with me that our mission is actually very clear. Our mission is as following: to find a set of conjugate directions. Because if we do that, and if we can do it efficiently enough, then our algorithm, just using the same line search code that we already kind of derived in our last lecture, just basically replacing those D vectors with some new guys, is going to converge in n steps, and then I have an algorithm that is no worse than Gaussian elimination. Does that make sense? Notice that if it takes me any more than like linear time or I guess quadratic time to find those conjugate directions, then I've lost, because then I might as well have done Gaussian elimination. And so far, it's not so obvious how to do that. Cool? All right. And so this conjugate gradient algorithm is based on some like totally magic observations. Namely, there's one, and I'll try to point it out when we derive it, where you just look at it and you think like, how did some guy guess this? And your guess is as good as mine. Like really, I don't see how it's maybe the most natural thing. But there's basically one really clever lemma, and the rest of it is just window dressing. So we'll see if we can get there. Okay. So in general, remember this notion of conjugacy is basically like a notion of orthogonality, right? It's like saying that all of my search directions di are orthogonal to each other with respect to this weird dot product here, right? This guy. And so there's a really reasonable way to find a set of conjugate directions, which is actually using, sadly for you guys, algorithm we already covered in this class, which is Gram-Schmidt, right? Or QR, or whatever you want to call it, right? Remember what the Gram-Schmidt algorithm does. It basically, it takes a set of vectors that we can't say much about. They're just arbitrary. It takes the first vector in that set and it just divides it by its norm so that it's length 1. It takes the second vector and projects out the first vector and then divides it by its norm. It takes the third vector, projects out the first 2 vectors, then divides by the norm, and so on. That's the Gram-Schmidt algorithm. And at the end of that procedure, I end up with a set of orthogonal directions. Yeah? So here's a really stupid way that I could potentially come up with a set of search directions for my conjugate gradient method. I could like come up with some arbitrary set of vectors, do the Gram-Schmidt algorithm. You can see, if you kind of write it down, in fact, we'll cover this in a minute. It's not so hard to extend it to this dot product. You just basically have to stick A's in the right place. And then, once you have that set of search directions, then you just kind of search along one by one by one. You just go down your big matrix of search directions. And by the time you're done with that, then you're guaranteed to find a solution of your problem. Now, what's the problem here? What's the issue? Yeah. Gram-Schmidt's too slow. That's absolutely right. In particular, what's the runtime of QR factorization, at least what we covered in this class? It's cubic in the size of my matrix. So if I do the algorithm as I've described, I might as well have just used one of the things we already did, and that kind of defeats the purpose, right? We're going to keep making this argument. Like there's a lot of kind of straw man things that happen along the path to conjugate gradient. But actually, this sort of kernel of using Gram-Schmidt, I think, is absolutely the right idea. And my best guess at how somebody guessed this algorithm to begin with is they coded Gram-Schmidt and then they looked back and said, oh crap, this thing is doing something really magical. That like, it turns out a bunch of terms in Gram-Schmidt go away. Ah, spoiler alert. Okay, so as we've described it so far, essentially the main issues we have is that Gram-Schmidt, for one thing, is potentially unstable. Like we haven't actually defined the things we're orthogonalizing yet. And moreover, there's sort of 2 things that are tangled up. So one, as Jonah points out, is Gram-Schmidt's already cubic time, so it's kind of pointless to run that and then use CG. You might as well run that and then just invert your matrix. And moreover, you have to store a set of orthogonal directions. Remember our point in CG, one of the ones that we kind of mentioned along the way, is that we want an algorithm that works really well for matrices that are easy to write like a piece of code for applying your matrix. which means you probably don't want to incur storage that looks like the size of your matrix. At that point, you lost. And so somehow, so far, this strategy doesn't feel so good. Make sense? Okay. But what we're going to do is use this as a starting point, and then we're going to kind of keep reshaping it and choose a very careful set of things to orthogonalize and see that actually Gram-Schmidt works very well for one specific choice of things to orthogonalize. This is so magic and cool. I hope you guys are excited because I think this algorithm is cool. And you should all implement it at home because it's just a few lines of code. All right, so now we're kind of gathering clues. Like we're putting ourselves in the footsteps of somebody who might have derived conjugate gradients probably in the 1960s or so. It was a dark time. They had to solve problems by hand. So like every iteration really, was a lot more painful than it is now when you write code. And now let's gather some more clues to help us along our path to deriving more efficient algorithm. Now, we're going to define an object called RK, which is going to be the residual of our problem at step K of conjugate gradient method, okay? So in other words, I'm going to define RK to be B minus A times XK, where XK is the kth iterate of our algorithm. Notice that in gradient descent, we took RK and DK, like the search direction, to be the same. But moving forward, we're going to think of these as two different things, that we don't necessarily have to use the residual of our problem as the search direction for gradient descent. Does that make sense? Some acknowledgement would be super helpful. Thank you. Okay, so let's do a little bit of math on our residual, because essentially what the conjugate gradient algorithm does is it notices that there's like this whole set of recurrences that happens when we apply gradient descent looking algorithms to this particular objective function that are really beautiful and useful to use. Now, in particular, I don't know why I wrote that arrow. We have the residual is equal to B minus AX. Oh, now I know. Okay, so let's look at RK plus 1. Let's see if we can compute the next residual from our current residual. Okay, so by definition, this is equal to B times A XK plus 1. Hopefully you all agree. Yeah, okay. But remember, how do we get xk plus 1? We take xk and we add alpha times our search direction. Right? So in particular, we know just by definition that this is b minus a times xk. By the way, this is where indices are going to get bad because I'm going to confuse which thing is a k and which thing is a k plus 1. So some of you guys are the index police, and I need you to start paying attention now. And so we have alpha k plus 1, dk plus 1. Right, so like this is the search direction to get the k plus first iterate. Alpha k, we actually have a formula for it. Remember, it's like the ratio of dot products. Cool? All right, so let's reparenthesize this expression the tiniest bit, because notice what happened. We have a b and an axk plus, right there. So that suggests maybe we should write this as rk, like that. And now what are we left with? Well, we're left with minus alpha k plus 1, a dk plus 1. Hopefully I did that right. Make sense? So notice that we have some nice recurrences here. Like we don't need to recompute our residual directly. We could have gotten it based on some products we kind of already had lying around. This is probably not the most exciting takeaway, but it is going to be a useful formula for us later. Now, specifically for gradient descent, we made a particular choice for our search direction. We chose this is where it gets confusing with indices. We chose the search direction for step k plus 1 to be the residual at step k. Right? And that was a choice. In fact, it was not a good choice, it turns out. Right? And essentially, that's how to derive the algorithm that we had in the previous lecture. And so for this particular one, of course, what do we get? We get an even nicer recurrence. We get that rk plus 1 is equal to rk minus alpha k plus 1 times a rk. Okay? Now, notice what kind of happens here. Let's say that I have some subspace that I know that rk is in. Right? Well, look at what happened. Essentially, I took rk and then I added or subtracted or whatever. Basically, rk times a. right? So if I have some space of vectors that I know that Rk is in, if I take the space of vectors and I pre-multiply it by A, I now know that Rk plus 1 is in the span of that set. We're going to formalize this on the board in just a second. Okay, so we have this nice recurrence. And essentially, one thing that you can do is apply this formula recursively. And what you conclude is the proposition on this slide, that if I were going to do gradient descent on f, here f is the function on the top board there, then if I look at the span of the set of residuals from 0 to k, that's exactly the same as the span of residuals that look like a times r0, or r0, a times r0, a squared times r0, dot, 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 a to the k times r0. And that comes from the fact that in each step of gradient descent, I take the previous residual and I multiply it by an a. Does everybody see how that proposition follows from this formula here? You guys are nodding, and that's actually very useful for me, and I appreciate that. Okay. Now pause here, because again, this is another one of these facts that we need to like cache in our brain, and we're going to pull back up when we derive our algorithm. There's a bunch of these little formulas that all get kind of melded together. Now, here's where things start to diverge. Notice that in gradient descent, we know that our span of residual, our span of r's looks like this thing on the right-hand side. And moreover, notice that the difference between x0 and where I'm at, right? So like the difference, like x0 minus xk is like somewhere in this span, right? Because on each step of gradient descent, I move along the residual. Does that make sense? And so when we put all of that together, by the way, this looks like a Krylov space if you're familiar with this kind of thing. That's not a mistake. What do we know? We know the following facts. We know that essentially xk minus x0, right? So the difference between where I'm at after k steps and the initial guy, I can say that it's actually in that Krylov space. It's in span, sorry, I want to make sure I get this right, of the initial residual, whatever it is, to a k minus 1 r0. Does that make sense? Like this is sort of a conclusion of this inductive formula here. Okay. Now here's the thing. It's in this span, but let's say that I optimized my original problem, right? So I optimized this objective function up here, but I restricted the difference. Essentially, I restricted x to be in this plane that I've written down there. Will I get the same result? Like if I get the global minimum constrained to be in this plane versus doing gradient descent? The answer is actually no. That essentially what we can show or not show, like if you just check this numerically, is stated a little bit more cleanly on the slide here. I see you, Jonah, but maybe we'll state this first and then get back to you. Is the following. I know that xk minus x0 is in that span somewhere, but what I don't know is that it's the minimizer in that span. I just know it's somewhere in that space. And that's sort of where gradient descent goes wrong. That like essentially, it's actually pretty easy for us to characterize the linear subspace that my current iterate is in, right? It's in this sort of interesting, like, you take the initial residual and just hit it with a bunch of times. But what I can't say is that I have the minimizer in that subspace. In other words, by taking a gradient descent one way, I might have actually erased a little bit of the progress that I made in some of the previous directions, right? And that's what we're going to try and fix. All right, Jonah.
I think I was just confused why we only go up to a k minus 1.
Ah, yeah, this is one of these really annoying things. Remember that I get xk by moving along rk minus 1. There's a off by 1. Incidentally, I believe the first edition of the book has all kinds of mistakes. I tried to fix them. You guys should read the chapter closely and let me know if they're still there. This is the kind of thing I'm totally blind to. I'm sorry, it's a condition. Yeah, I don't know. I'm sure it's in a medical dictionary somewhere. Okay. Let's say that I could manage, I see it. Let's say that I could manage to get this equal sign somehow. Notice that in that particular case, I have guaranteed convergence in n steps, right? Because after the nth step, at that point, my subspace is all over n, and my algorithm is done. And in fact, if you look back to that lemma that we proved before, showing that like moving along conjugate directions is convergence in n steps, it basically amounts to showing exactly this identity for that particular space. Yes?
I just want to clarify this statement. Are you saying that like the iterates xk are in that span, but the optimum might not be?
Not quite. What I'm saying is the iterates xk, at least after you subtract off x naught, are in that span. But they're not the place that gets the smallest possible value of f, even if you restrict yourself to be in that span. Right? So in other words, like if I look at this plane blah, words are hard. If I look at the plane that is spanned by the last however many iterates, right, and I take a slice of my objective function through that plane, right, somewhere in that plane there's a minimum value of my objective function in that plane, right? And there's some hope that my algorithm would have found it because it's already kind of searched directions in that plane. But sadly for gradient descent, that's just not what happens. You end up somewhere else, right? And so our goal is to derive an algorithm where that doesn't happen, where like at every step, you are in the minimum of the plane of directions that you have looked at so far.
I see, I see.
Yeah.
So this is basically to say that like gradient descent just really isn't helping you here.
Yeah, it's basically a complicated way of saying gradient descent kind of sucks.
Yeah.
Yeah. Mm-hmm. Yes.
Like, so in a 2D case, we had that picture of a zigzag.
That's right. Which is a very clear example that this isn't true, right? Because if this were true after 2 steps, I would have converged. Yeah, that's right. Yeah, so in 2D, that's exactly right. That's actually a great comment. In 2 dimensions, we ran gradient descent and zigzagged. But obviously, if this fact were true after 2 steps in 2D, the algorithm would have converged. Yeah, good point. Any other things? I'm so glad you guys are thinking critically. You should fight with this algorithm because it's easy to become complacent. Okay. All right, so here's going to be our outline for conjugate gradient algorithm. We're going to somehow generate a bunch of search directions vk, one after the next, successively. And then the rest of our algorithm looks exactly the same as it did before. Right? This formula alpha k is exactly what we derived in our previous lecture. This is just quadratic line search on a long line. And then I update x. And by the way, I can update my residual while I'm at it. Yeah? Why not? Okay. Notice that I am updating my residual separately from updating v. That, like before those were coupled together, now I'm going to do them separately. Because it's going to be useful to have the residual around. It's just not going to be the direction that we search along. Cool? All right. Now, greedily, when we write down this algorithm, essentially what we're hoping to do is, greedily, we'd like to have an easy way to make a bunch of conjugate directions. And moreover, just for fun, like if we're trying to be catty and we want to like say that we're doing better than gradient descent, then maybe in fact we put a second condition on our VKs, which is that their span is exactly the same as the span of the like sort of the directions that gradient descent has seen so far. Right? This second property is a new one. This is me being greedy. Because what does this say? This says in every step of my conjugate gradient algorithm, I do strictly better than gradient descent. Right? Because I'm in the same subspace, but I am optimal in that subspace. Right? So that would be kind of nice, comparatively speaking, to make sure that it's not the case, for example, that 10 steps of gradient descent is actually better than conjugate gradient, and then 11 steps it flips or something like that. Like if we have property number 2, that can't happen. Every single step of this algorithm is better. Does that make sense? Okay. Right, and again, actually these 2 points on the bottom are the reason we want the 2 points at the top. The first guy gives us that we converge with like a capital C in n steps. And the second one says that we always do better than gradient descent. By the way, I should note, when I say converge here, I mean before like dealing with numerical precision, right? Like in the presence of rounding, conjugate gradient won't converge in n steps, it'll kind of converge in n steps. And in that particular case, some things can go wrong. And we'll talk about some tricks that people add to CG so to kind of stabilize it numerically, because it's actually very subject to drift. Okay, so here's our straw man algorithm. Here's one that satisfies property 2, but does not satisfy property 1, right? Like in particular, kind of going back to an observation we made before, let's say that I wanted a set of vectors that has the second property. I could get it quite easily by doing a simple thing, which is just doing Gram-Schmidt on the right-hand side of that equality. Do you see that? Like if I do Gram-Schmidt on R0, AR0, dot, 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 a to the k minus 1, R0, then by definition, I have a set of conjugate directions whose span is the same. Does that make sense? So here is dumb algorithm number 1. It has a name, apparently. Just, that's fun. This algorithm is called the method of conjugate directions. I really want to say conjugate gradients, but that's actually not the case. And the method of conjugate directions does the following. It says, oh, in every step of my algorithm, I'm just going to compute ak to the minus 1 times r naught, right? This is the new thing I just added to my span, and then just project out all the search directions I've seen so far, right? This is the Gram-Schmidt formula. And now what do I know? I know that this vk is necessarily orthogonal with respect to a to all the previous v's, because I kind of just did it with this sledgehammer. And moreover, it's in the span that I wanted because I literally just took the vector I haven't seen yet and added it to the list. Does that make sense? All right, now at this point, you guys should be looking at this formula because you've seen lots of things like this in this course and should immediately be allergic to it for like 12 different reasons. Does anybody want to give me a few? So let's say that my matrix is like 50,000 by 50,000, right? So here K could be like 40,000. So what do you think the difference between a to the 40,000 times R naught and a to the 40,000 and 1 times R naught is going to be? They're pretty much the same vector. At that point, it's probably converged to the principal eigenvector of the matrix. And so like Gram-Schmidt orthogonalization is basically working a little tiny numerical epsilon at that point, right? Because my vectors all look kind of the same, but somehow I'm trying to orthogonalize them, right? So that's one issue. The second issue is computational. Obviously, I don't want to multiply anything by matrix K times. That one's kind of fixable, right? Like you could keep R around and just keep pre-multiplying it by A in each step. So I'm not too worried about that. But there's a more important storage issue, which is that I got to remember all the V's. Do you see that? So in order to get Vk, in order to apply this formula, I need V1 through Vk minus 1. And so essentially the storage capacity that I would need to run the algorithm in each step grows, right? So if I have a 50,000 by 50,000 matrix, in order to get to step 50,000, I have a whole 50,000 by 50,000 matrix of V's that I got to keep around. That's not so good. Does that make sense? So those are the problems we're going to try and address. We're almost there, I promise. Yes?
Like in general, as K gets big, how do you avoid like overrunning your n squared budget, basically? Are you doing what you said, just multiplying the vector by the matrix and thus only burning like n squared?
Well, so there's two different questions. I mean,
The actual matrix multiplication, that would be greater than n squared, right?
that's right. I mean, there's any number of issues here, right? One of them would be matrix multiplies. I think the larger one here is just numerical stability. Just A, you have to remember all the V's, and B, all of these R's look basically the same, so you're working in very small numbers. So these are all reasons not to use this method. That's my point. Yeah. And so what we're going to find is that like essentially two simple fixes to this method are enough to make it work really well. Just so cool. This is such a cool algorithm. This is just neat. Okay, so as we see, essentially this looks like the largest eigenvector of A, so projection is not going to work too well. And moreover, we got to kind of store all these vectors, which defeats the purpose of our algorithm where we kind of want the storage to stay constant in every step. Okay. Okay, so we're going to make a small adjustment, and then we're going to make a big adjustment. But what we're going to see is the big adjustment is kind of a consequence of the small one, which is the following. When I did Gram-Schmidt, did I really need to use a to the k minus 1 R naught as the thing that I orthogonalized? The answer is no. The only thing I really needed was something in the span of the bigger set of vectors that wasn't in the span of the smaller set of vectors. Let me write that out on the slide. In particular, notice that if I took any W in the set that I've written on the slide here, I could have applied Gram-Schmidt and gotten a valid search direction. Do you see that? Because essentially, this difference is saying, okay, I look at the space of directions that I need in my current step, so that's R naught to a to the k minus 1 R naught. In the previous step, I looked at R naught to a k to the minus 2 R naught, right? So any W in the difference between these two things will lead to a valid search direction after a Gram-Schmidt method. It doesn't have to be exactly that vector on the end of my list. Does that make sense? And in fact, up to scaling, the direction is unique, right? Because I have this giant plane, and now I just add one additional kind of direction to that plane, which is a to the k minus 1 R naught, right? And so after projecting out that whole plane, I'm guaranteed to get something parallel to that last direction. That make sense? So what we're going to do is cleverly choose a W that makes this projection a little bit better behaved. Yeah? Yes?
If we're still in that direction, is it not still just going to be the principal eigenvector?
Yeah, it's going to look awfully close. It won't be the principal eigenvector because we're sort of orthogonalizing in every step, but it is the case that it actually is going to do kind of an interesting thing, which is converge to something that looks like one of the eigenvectors. Yeah, if you look at CG, the search directions are kind of cool to plot and look at. That's absolutely right. All right, so, sorry, I fell behind on my notes. Yeah, okay. So what we're going to do is we're going to say, okay, so in particular, notice that we had a particular formula for obtaining the next residual from the previous one, which for some reason I just hid behind. Right, so remember that to get RK plus 1, I took RK and I subtracted some multiple of A and the previous search direction. Does that make sense? So here's going to be the kind of cool idea. Notice, in fact, there's like a few different ways that we can argue that. Notice that our previous residual was kind of in a particular span, and now I multiplied by A, right? So if you think about it, what's going to end up happening is they're going to introduce just enough information to move into that subspace on the left. And in particular, what I can do is rather than using a to the k minus 1 times r, I'm just going to use my residual as the thing that I orthogonalize. Here's a different way to understand why that's a good choice. Remember that what is the residual at the end of the day? It's the error of my linear system, right? It's a vector that like it's the backward error. It's b minus ax, right? Let's think about what would happen if that thing, purely all of its components were in the span of the stuff that I've already seen. Then actually I've sort of contradicted the derivation of my algorithm, which says that I'm optimal in that span. So kind of necessarily, I better have a component outside of it, right? So in particular, here's what I'm going to do, is I'm going to implement this method of conjugate directions, this guy, but rather than having a to the k minus 1 r naught, like this piece of the formula here, I'm just going to replace it with my current residual rk. So that's going to be our first clever idea, is the following. We're just going to take the currents vk before projection to be rk minus 1. Oops, I'm sorry, there's a bit of a typo on the slide here. I apologize for that. The right-hand side of the arrow is wrong. Can somebody remind me after class and I'll fix it so I don't have that next time? What I mean is that vk is the projection of rk minus 1 into the orthogonal subspace of the search directions we've seen so far. So in other words, this formula down here. Does that make sense? So notice, like in some sense, what I've done is made like the world's smallest edit to gradient descent, right? So remember that gradient descent takes vk to be rk minus 1. In our new algorithm, what we're going to do is take vk to be rk minus 1, but we're going to project out all the previous search directions before we use it. That's the only difference. Yes?
What's the typo?
Oh, the typo is this thing. This is true for gradient descent. But that is not true for conjugate gradient. For conjugate gradient, vk, obviously, in fact, I wrote a formula right here, is the correct one. Yeah, yeah. Yes, on. Absolutely, but we which is what we want. Remember, we want it to be in the same subspace as the set of residuals. Yeah. Okay, so far, what have we done? We've essentially said, okay, rather than using this, oh sorry, I guess the stuff on the this stuff on the top of the slide here to compute our search direction. Instead, we're just going to take the search direction that we would have done with gradient descent, like r. But before using it, we're going to project out all the previous directions we've seen so far to make sure that we maintain this conjugacy property. Okay? Now, that eliminates some of the issues, like we're no longer computing big powers of a, we're just using r. And as On points out, we sort of are, like kind of implicitly, but at least we're not like actually doing it in every step. But still, this algorithm is too slow. I mean, one step of this algorithm, I have to have a big for loop over all my previous directions, right? And so this thing is quite expensive. In fact, a single step of this thing is going to take something like cubic time, so this is no good, right? So this is one of these things we're going to do. We're going to keep taking an algorithm, reshape it into another bad algorithm until we notice it's actually a good algorithm. Okay? So far, what we've done, we've taken gradient descent, and we've just made a small edit to it, which is that before we do our search direction, we project out all the ones we've seen so far. Cool? All right. My phone is going crazy. I really got to turn it off before class, like I tell you people to do. All right. Now get excited. There's like a magic lemma that is what makes conjugate gradient method work. And I think my best guess of how somebody derived conjugate gradient method is as follows. Notice that like if you just made the observation that if your directions are a conjugate, you converge, then this thing that I've written here is something that I think you could have reasonably guessed, right? Because like in some sense, gradient descent just searches along rk minus 1. So kind of the stupidest thing you might think of doing is like, oh, well, gradient descent is pretty good, but I know that if they're just a conjugate, then like somehow it should do even better, so maybe I just project it out before I take that step, right? And I think somebody could have reasonably coded this thing up, and like, and indeed, in n steps, this thing converges. It's a slow algorithm, but like it's kind of cool that it works, right? But then you look back, and you look at these coefficients here in this sum. Like, what are these coefficients? These are kind of like the projection of our current residual onto the span of the previous residuals, in some sense. Certainly the span of the v's. And there's a numerical experiment, which if I were a better professor, I would have coded before class just to show you so we could have a big reveal, but I didn't, which is as follows. What do you think is going to happen to most of the terms in this sum? This is the miraculous thing about conjugate gradient method. they don't quite cancel, but they're actually, it's better than that. They're just 0. So if you run this algorithm, what you will find is you can compute that giant sum that you would do in Gram-Schmidt, where you have to remember all your search directions. And then what you're going to see is after 2 terms in that sum, it's just a bunch of zeros. This is just incredible. And this is the little lemma that we're going to prove today. It's a little bit technical. By the way, hopefully you figured out by now when I say that, it means I'm about to get the proof wrong, so get excited. But essentially what we're going to prove is the following. If I take my current residual and any of the previous search directions, right, that's the V's, and the residuals are K, then the inner product of those with respect to A is equal to 0 for all L less than K. Now this is one of these cases we have to be a little bit careful with our sum, right? So if we look back at the previous slide, there will be one term in this sum for the exact, like the residual we just saw in the previous step, but then all the other terms are going to go away. This is so cool. This is just magic. Like this is the one little magic lemma that happens. And as far as I can tell, somebody just got it by coding it, looking at the coefficients, being like, oh dang, these are 0, right? Because like the proof itself is just kind of simple induction. It's a little bit messy, but you know, it's not terribly complicated. But the observation itself, as far as I can tell, the best way you could get there is just empirically. Okay. Any questions about what we're about to prove? Yes.
I just want to clarify. So on the previous slide, like that's the algorithm that converges in steps.
That's right.
Because they're conjugate, not really like.
That's right. Yeah. So this thing converges in n steps because we just sledgehammer to get conjugacy, right? Like we just projected stuff out until they're a conjugate. The magic thing that happened here is that our projection formula just happens to be much simpler. Yeah. Right? It's this like very intricate little construction that we've made. Okay. Now, let's prove this lemma. Or at least like try for a few minutes, get bored, and then tell you to read it home. That's my goal. Okay. I noticed I was like kind of paging through the last time I taught this that I cleverly used the board, proved a bunch of theory, like proved a bunch of useful formulas and then erased them and then immediately needed them as soon as I wrote that. So I'm going to try not to do that today, but we'll see if we manage. Okay. Hopefully by now we can all remember this form for our function f. Okay. So it's important not to think too hard if we write proofs like this. In particular, we are going to prove, oh my God, oh no, I hate this classroom. Actually, that's not true. I hate all MIT classrooms. Okay. Right. What we're going to do is prove this just by induction on, okay? And notice that like I was secretly kind of leading up to that the whole time because like we've been proving a lot of little useful recurrence formula that are going to show up in this argument. Okay. Now, first of all, the first thing we should do is check our base case, right? So maybe we choose k equals 1. And here's my proof of the base case, it's a check mark. Because essentially there's nothing to prove in that case because there are no previous search directions. Okay? So basically the only thing that we need to do is show the inductive step. So in particular, we're going to assume k is greater than 1 and that the result holds for all k prime that are less than k, right? You've probably, if any of you I hope that you've all taken some introduction to proofs class before stepping foot in this classroom, and you've probably written some version of this sentence about 400 times. Yeah, okay. So here's what we're gonna do. We're gonna separate this into 2 different cases. One is when L, remember that L in our theorem is like the search direction, is like a lot smaller than k. And then one is when L is just a little smaller than k. We're going to show that we need 2 different arguments to make that work. Okay, so first, so we're going to do 2 cases. I'm going to try and reshuffle a bit from the proof in the book. We'll see. That's dangerous, of course, but I think I can make it a little more streamlined. Okay. Case 1 is when L is less than strictly k minus 1. Notice in the statement of the theorem, we have that L is less than k. So here, we're going to put like a bigger gap between L and k. Alicia, what can I do to help you out? What, you can't read this mess? All right. Result holds for all k prime less than k. Yeah. Yes. Yeah, I haven't written anything yet. All right. I haven't actually proven anything. All right. So, right. So here's what we're going to do. Remember that we have this useful residual update formula, right? And in particular, that feels kind of useful here because essentially I can write RK in terms of the previous Rs, but we know the result holds for the previous Rs, right? So it seems useful to plug in that formula here and see what happens. So in particular, we have RK inner product with VL. By the way, I'm going to start omitting the subscript A. Hopefully that's okay. Yeah. Well, what is this thing equal to? Well, if I plug in the recurrence, which for once I didn't erase, it's up there. Notice that here's what I'm going to get. I will get that this is equal to RK minus 1 inner product VL minus alpha K times A VK inner product VL. Right, and that's just because RK is equal to RK minus 1 minus alpha A VK. Right, so it's just the recurrence we wrote down. Are you with me so far? Fabulous. Okay. Now here's kind of a useful fact. Let's expand this thing the tiniest bit. In particular, it's a little bit annoying that our A is in front of VK and K is the big index, right? So here's a thing that we can do. This expression by definition is VK transpose A VL, right? Because remember that our inner product is with respect to A. Cool. And now remember that A is symmetric, so this transpose isn't actually doing anything. Yeah? So here's a different way to parenthesize it. I could take this A, which used to be the kind of inner product A, and parenthesize it this other way. And what I'll get is that this is equal to the inner product of VK times A VL. Does everybody see the sleight of hand that I just did here? Essentially, I just moved the A over here. If you're a fancy mathematician, you might say that there's like a self-adjoint property that's happening here. Any questions? Now, why might I want to do that? What was that? Well, notice that, like, okay, here's kind of a funny thing that we can do, which is the following. I claim that if we look back at our algorithm, what do we know? Well, we know that A times VL is in the span of V1 to VL plus 1. Why is that? Well, VL is clearly in this span without the very last guy, right? And when I multiply by A, remember that like every time I multiply by A, I'm just kind of adding one of our things to the span that we've worked with in this algorithm. And so in some sense, the span of our search directions, A times VL is definitely in that space because this is exactly the sort of new update for our residual, yeah? Well, here's the thing. I'm taking the inner product between K and A times VL, or VK and A times VL, yeah? You're making a finger wag. Did I do something wrong? No, okay. What was the whole point of our conjugate gradient algorithm? Well, it was to make a set of directions which were conjugate, yeah? And in particular, what do we know? We know that VK times V, I'm running out of indices, J is equal to 0 for all J less than K, right? Just by construction, that's true, right? Yes, some agreement? Okay, so let's take a look. A times VL is in this span of the previous V's that I've already seen, each of which is orthogonal to VK. So in particular, what I can conclude is that A times VL, inner product VK, is equal to 0. Does everybody see that? Because essentially, this guy I can write as some linear combination of all of these vectors, each of which is orthogonal to VK. Cool? So notice what I just did. This term goes away. This is just 0. Fun, we're halfway there. Living on a whatever. Okay. Right, so that's 2. Now, let's look at this term. This is the inner product between RK minus 1 and VL. what was our inductive hypothesis? Well, take a look at the statement of the theorem. It's precisely that, right? So this term is also 0. Okay, so at least when L is less than k minus 1, we have verified our fact that we got 0. So we're almost there. We just need a special case for L equal to k minus 1. Yes?
I have 2 questions. The first is, what was the construction of VK, VJ, of the inner product equal 0?
Oh, this is just by definition of the algorithm. Like, if you look at the what we did here, right? We applied Gram-Schmidt in the bottom there,
Yes.
and that the whole point of that is to make this property true.
Okay.
Yes.
But I got lost with the letters.
No, yeah, that is very understandable.
Yeah. The other one is, so we use the recurrence above, which we define by like saying, like, if we were to use gradient descent, this recurrence holds. It's covered by the board.
To be absolutely clear, the recurrence, actually the one that's not covered by the board, is always true.
Okay.
So here we've chosen a new search direction, like these V's that we've orthogonalized. What isn't true is that we can't stick an R for that second D there. Yeah, that's absolutely right. Okay, so we're done with half of our proof. The last thing we got to do is do a special case. This is for L is equal to k minus 1. This one is easy to get wrong. I think I got it right this time. I double-checked my notes this morning. We'll see if we get it right together. So remember our residual update. This is our favorite formula here. In fact, maybe I'll just replicate it. So we have, in this particular case, rk plus 1 is equal to rk minus alpha k plus 1 a v k, like that. Cool? All right. So what we're going to do is something sneaky, which is the following. We are going to look at the difference rk minus 2 minus rk minus 1. This is kind of fun. Like basically all the arguments about conjugate gradients are just like weird recurrences that you have to derive really carefully and then like check your indices 1,000 times. Okay? Now, if you think about it, if we apply our recurrence, this is rk minus 2 minus, now let's apply this residual here. We're going to have to be careful because we're now like shifting everything by like 3 or something, which is kind of annoying. And what we're going to get is rk minus 2 minus, oh no, I got lost in my notes. Alpha k minus 1, a v k minus 1. Right? This is just an application of this identity where I've shifted the indices accordingly. That make sense? By the way, this is kind of unsurprising what's happening here. Notice now these guys cancel, and what I'm left with is alpha k minus 1, a v k minus 1, like that. Okay? So in other words, we can reshuffle the tiniest bit and say, a v k minus 1 is equal to r k minus 2 minus r k minus 1 divided by alpha k minus 1. Cool? All right. Now, so far this just feels like a fun fact, because it is. There's like so many recurrences you can prove about conjugate gradients. You can do this all day. It's going to get worse when we precondition. Okay. Here's what we're going to do. We're going to pre-multiply by rk transpose. So we're going to take the expression that we have here. We're going to pre-multiply it by rk transpose. Why should I do that? Well, notice that I have a vk minus 1. So if I do rk transpose a vk minus 1, that is exactly the thing we're trying to check is equal to 0 in this case. Everybody think about that sentence for a second. Look at the theorem. Look back here. Make sure you agree. Okay. So what did we learn? We learned that rk inner product vk minus 1, notice that is exactly this guy pre-multiplied by rk, is equal to k inner product rk minus 2 minus rk minus 1. I wrote like 3 r's. My bad. Divided by alpha k. By the way, if you're wondering, the alphas are kind of like not doing anything in this proof. They're just annoying. But I have to keep copying it. Like that. Okay. Now this thing, let's think about it. We're going to keep using kind of a similar argument. These residuals here, actually, maybe not for now. Okay. So by conjugacy, what do we know? We know, oh no, I used the board in the back that I can't erase, or that I can't. That's okay, we'll just move over here. And now here's the kind of fun thing we're going to do in this argument. We're going to use like a tiny, tiny bit of calculus, which is a little unexpected because it feels like we're like pretty solidly in linear algebra land right now. But I found this is the most efficient way to prove this, which means it's probably wrong. So by A conjugacy, what do we know? Well, we know that xk is optimal in a particular subspace, right? In span of R0 a k plus a k minus 1 rather, R0. Or that was our construction. We want to stay optimal in every step of our algorithm. Now, here's the thing. From our residual formula, what do we know? We know that these vectors themselves are in the span of R0, A remember, because we just basically applied Gram-Schmidt to these vectors to get our search directions. Okay, so what do we know? We know xk is optimal in this span, and moreover, we know that these two vectors that we're subtracting are also in this span, so this feels kind of good. It feels like we're in like a nice universe. Our proof is almost done, which is good because I'm sweating. So in particular, what do we know? Here's kind of a little picture that we can think about. Remember that like, in general, our gradient is 90 degrees to the level sets of our function. And in particular, what we can conclude is that Rk has got to be orthogonal to, oops, sorry. Oh no, I'm going to abort that sentence. We're going to try again. Sorry, my bad. Here's what we can say. The gradient of f, like just maybe a minus, at xk is orthogonal to the span. And let's think about why this is the case. Well, xk is optimal. I cannot make my objective any better in that subspace, right? So what does that say? And remember, the gradient direction is how to make my objective locally a little bit better, right? Well, if I know that I can't do any better in this subspace, then necessarily the directions that make my objective better are orthogonal to that subspace. Yes, on. With respect to the dot product. That's exactly right. And notice there's a dot product right here. See what I did? Isn't this cool? So what is minus the gradient of xk? Well, it's exactly b minus a xk, which is equal to rk. Okay? Everybody with me so far? This is our like little itty bitty bit of calculus. Right? It's just saying that like, so far all of my iterates are in this plane, and I know I can't do any better in this plane. So necessarily my gradient points me out of that plane, right? And moreover, my old residuals were in that plane. So what can I conclude about this dot product here? I can conclude that it's equal to 0. And that, thank God, completes our proof, right? Because remember, this inner product of when the smoke clears was exactly the thing we were trying to compute to begin with. So I'll let you guys review that proof a little bit at home because it is a little technical. But essentially, the basic point here is that we keep using the fact that our residuals are in this funny span here, right? Which is true in this algorithm because all we did was essentially apply some version of Gram-Schmidt to exactly this set of vectors. And then every time we did that, we were just really, really careful with indices to kind of show that every step of this method has to kind of move out of the plane of the stuff that we've seen so far. And that's really what's being reflected in this inner product here. Yes, Hamid. Yeah. So this is actually what we proved in our previous lecture. Remember, we showed that so long as our search directions are conjugate to one another, then we maintain optimality in the plane of the search directions we've seen so far. Yeah. Good question. Any other? This is one of these proofs that like feels uncomfortable because I'm uncomfortable. But if you look back at the book and you review it a few times, you'll see that like it's just barely correct. That like this is one of these things where like if any one of these indices were a little bit off, then you wouldn't get the right thing. But that's okay. Okay, so what does that mean? That means that essentially, if we go back to our method of conjugate directions using the residuals, then every term in that sum that we had before is equal to 0 with the exception of one previous guy, which is when the two indices, notice the r and the v, have the same subscripts here, and we only showed it for less than, right? So we essentially only have one term left in that sum, and now we are cooking with gas, because essentially this leads us to the conjugate gradient algorithm, which is as follows. What am I going to do? I will take my current search direction to be the current residual just minus that projection. And what we notice is that we didn't actually need a sum to do that giant projection. We just needed one term. All we had to do was project off the last guy. This is the sort of miraculous property of conjugate gradient. And then all the rest of these steps are just what we had before. Now, what is the complexity of this formula? Well, now I have eliminated the sum in my projection. So evaluating VK, I do need multiplication by A. That's kind of hiding in the inner product there, but if I do it just right, I only ever need multiplication by A. I don't need to loop through a bunch of previous guys and do it for each one. So now I have quadratic complexity per step. Do you see that? Moreover, essentially the whole point of this ugly proof we wrote down is that the set of VKs we have are conjugate to one another. So after n steps, this algorithm is guaranteed to give me, up to numerical precision, the actual solution of my linear system. Yes, John.
If we say that this is quadratic complexity per step,
Mm-hmm.
makes a maximum of n steps to converge.
That's right.
Are we still n cubed then?
That's right. We didn't do better than Graham-Schmidt, but we didn't do worse. Now, the beauty of conjugate gradient is that typically you don't run it for n steps. That essentially this algorithm has this nice property that's sort of the best of both worlds, right? Because the whole point was we derived it from like a line search procedure, meaning that if we stop early, the objective function decreases in every step, right? In fact, it's optimal in the subspace of residuals we've seen so far, which if you think about it is sort of the subspace you'd want. And so typically what people do is they find that CG converges quite quickly in the numerical sense, but it also is never worse than Graham-Schmidt in the sense that if you run it for n steps, you really do solve your linear system. So it's got sort of both possible properties. Now you might ask I see your hand, if you might ask a different question, which is what is the convergence rate, which is kind of funny. In some sense, the convergence rate doesn't matter because it converges in a finite number of steps. So strictly speaking, convergence rate is kind of a useless thing. But what you can show is that the objective function decreases at a rate that kind of looks like the condition number of your matrix with a square root over it. Remember, what's argued in the book, we skipped the proof in class because I'm lazy, is that gradient descent, A, does not have the property that converges in a finite number of steps, and B, the objective function decreases at a rate that kind of looks like conditioning. So now we've actually managed to do with a square root of condition number, which is better, right? That's a happy thing. Yes.
If A is like highly sparse,
That's right.
is that the only term where we're quadratic instead of just linear then? And so
Yeah. So notice when I say quadratic, I mean for a full dense matrix A. Typically the application of this A sometimes only has a linear number of elements, in which case every step of this is even faster, right? And it's not obvious how to do Graham-Schmidt in a way that's faster than n cubed. Whereas this thing is basically really kind of looks like n times the complexity of applying A, whatever that would be. Now, in this is not the form, like if you look on Wikipedia, this is not what they say conjugate gradient is. Essentially, they reshuffle these formulas a little bit to reduce the number of times per step that you multiply by A. This is just an algebra exercise. I'll show you on the slide in a second. I don't think it's worth deriving on the board because it's just a question of like writing these formulas down and parenthesizing a little different. But yeah, I think you can basically end up making this algorithm so that in every step you just have to multiply VK by A, and that's it. And then you keep that vector around. Okay, so this algorithm has so many cool properties. It remains optimal in every step. The F is actually upper bounded by the F that you get from gradient descent in every step. Remember we mentioned that earlier, meaning that like this is strictly better algorithm than gradient descent, and moreover it converges in n steps. Unfortunately, it's hard to visualize because in the plane, the property that it converges in n steps mean all the diagrams kind of look like this. But the good news is that like, you know, it doesn't zigzag anymore. It just kind of like, ta-da, like bounces you right into the minimizer of this problem. Here's the form that people typically use for this algorithm. It's a little bit different. Essentially, all this is doing is taking formulas from the earlier slide and trying to factor out, like you'll notice that you compute A times V a bunch of times. And so like what you can do is basically just store that and then reshuffle these expressions a little bit to avoid having to compute it more than once. And so you can see in this form, essentially you only need one application of A in every step because it appears here and there and nowhere else, and both times are by P. Yeah. So this is the sort of typical form that you see. Incidentally, one thing that people find empirically is that this residual update formula becomes a little bit dangerous if you run it long enough, then you can kind of accumulate numerical error. And so it's sort of in common practice what people do is once every like say 100 iterations, this is a made up number, rather than using this update formula, you just recompute the residual by doing b minus a times x. Notice that doesn't affect the complexity of this algorithm, but it does incur one additional multiplication by a, which is why people don't do it in the vanilla form here. Yeah. That's purely a numerical thing. It turns out that that's enough to fix the instability of this algorithm. You just need some way, because like notice that there's actually something kind of weird about this. Remember, our whole point of this algorithm is to solve ax equals b. Yeah? Do you see b anywhere here? No, and that's because b only appears in the very first residual, and then everything just gets updated with this kind of recurrence. And so that's why it's good to like occasionally not use this update formula, but to just compute it directly from b, because in some sense it's very easy for this algorithm numerically to kind of forget the right-hand side of the linear system just by rounding. Like in theory that's not needed, but just in practice sometimes it is. Now to go back to Jonah's question, typically you don't run this thing all the way to convergence. Instead you look at maybe the ratio of the length of residual in like step k to the length of residual in step 0, and you stop when it's below some acceptable threshold. And in fact what you can show is that this thing, the convergence rate, kind of looks like the square root of the condition number, which is a heck of a lot better for ill-conditioned matrices. Now, oh man, I talked too much. I think we can do it. Okay, actually we started a couple minutes late. Okay, I promise we're gonna go to 28 and then I'll stop. If you have to leave, then fine. Now, here's the thing. Convergence of gradient descent, or conjugate gradient method, directly looks like the conditioning of my matrix. But here's kind of a clever idea. Notice that the condition number of my matrix A is clearly not equal to the condition number of my matrix P times A for just some arbitrary P. So for example, let's say in some ideal universe, P is A inverse, right? Then like clearly the condition number of A inverse times A, which is 1, is a heck of a lot better than the condition number of A, right? And moreover, convergence of conjugate gradient direction algorithm directly has to do with conditioning. And so what's very common to do is to say, can we come up with some kind of quick approximation of A inverse that I can use for P so that when I apply conjugate gradient method to the system on the bottom of the slide, it converges more quickly. This is a procedure called preconditioning. It happens all over the place. The basic idea is that all of the algorithms we've covered so far in this class that are iterative, like Newton's method, even eigenvalue iteration, incidentally, their convergence rate has to do with conditioning. So the closer I can get of my condition number to 1 by just rewriting my problem in some equivalent fashion, the more quickly I expect my algorithm to converge. Does that make sense? Now, in fact, we can even prove a bound on that. So in particular, now here's going to be the basic challenge, and this is probably what we'll do in our next lecture, but I will try to convince you that conditioning is a good idea. Now, can I apply conjugate gradient method to P times A? Jonah's nodding because he's a nice guy, but let's think about it for a second. Remember, what do I need for conjugate gradient to work? I need particular properties for A. What were the? Yeah, I need it to be symmetric and positive definite. Now, A might be symmetric positive definite. Maybe I even take P to be symmetric and positive definite. Their product might not be. So here's going to be our really sneaky trick. Oh, this is so sneaky. Okay. So here's what we're going to do, and maybe we'll stop after this thing. So this is what we'd like to do, but it's not SPD anymore. Let's say that I take P to be a positive definite matrix. So in particular, once again, I can use my similar proof technique, which is I can say, well, I know that there's a Cholesky factorization for P, and P inverse, by the way, just for convenience, even if I don't use it. Yeah? So in particular, let's say that I factor P inverse using Cholesky. We're going to prove kind of a fun thing. Oh, that's fun. Pareto distribution. It's always a surprise in this class. Okay. which is the following. Essentially, we can claim two things, PA and E inverse A times e to the minus transpose have the same eigenvalues. So in other words, if PA is kind of a well-conditioned matrix, then this weird thing will be as well. Okay? Now here's going to be our proof. Let's do one direction really quick. X lambda x. Notice that this matrix clearly has eigenvectors because it's symmetric. The other one might not. But in particular, if we pre-multiply this guy by E minus transpose, like that. Okay, so what is this object? Well, this is exactly P by definition. And notice that I have P times A times some vector is equal to lambda times that vector. So in other words, this guy is now an eigenvalue of P times A, right? And so what this allows us to do is to prove a condition number bound. So in particular, what is going to be sigma max of PA? Well, one thing that we can do is say, okay, by definition, this is the max over all unit norm vectors. So by the way, this is the, oh yeah, no, that's the, never mind. P times x like that, right? So in particular, if I plug in any x here, that is a lower bound for this max. So here's what I can do. I can say, aha, well, then this is greater than or equal to P times x, where x is sort of like the x corresponding to the maximum eigenvalue, right? And this thing, by definition, is just, and similarly, the smallest singular value is bound to the other direction. So here's kind of the argument that we'll leave you with for today, which is the condition number of P times A. Well, remember that it's equal to sigma max over sigma min, I guess, of PA. Yeah. Which by an argument here is greater than or equal to, but like roughly on the same order as lambda max over lambda min of PA. But remember from the argument we have on the board, oh no, these boards are so heavy. There's just enough of e to the minus 1, a e to the minus transpose, like that. Yeah? Okay, and now this matrix, unlike PA, is symmetric, so its eigenvalues and its singular values are the same. So this is actually just the condition number of e to the minus 1, a e to the minus transpose. So all this is to say that if I take P to be kind of like the inverse of A, I also expect this matrix to be well conditioned. That's my point. So that suggests an algorithm. I promise we're done after this. 2 more seconds. Which is as follows. At least in principle, I could solve this system here, and then I could just recover x. The only problem is to do this algorithm, I would need access to E, which I don't want, right? Because that's expensive algorithmically. So here's what's done in the book, which is absolutely magical. So I could apply conjugate gradient to this problem, like number 1 here. I could just, every time I see an A, I now put this weird matrix. And what I get is this expression on the board here. Notice that in here, there's basically only a few things that involve E, and every time I see them, it happens to be next to an A. So here's the kind of magical thing that you do in this technique is you just reparenthesize this expression, and you show that it is exactly equivalent to the following algorithm, which just puts P's in clever places. So I'm going to let you guys read the book because I'm low on time. But the basic argument, again, is as follows. Rather than solving AX equals B, we solve this thing where basically I've conjugated with E and then done a little bit of substitution to make sure that I kind of undo that transformation. In principle, I could do conjugate gradient on this matrix, And then what we find is that is exactly equivalent to some other algorithm involving P times A, where all you do is you just reparenthesize all the formulas from CG in a clever fashion, and you never actually have access to E. So anyway, that's just a preview of the argument that's in the book. I'll let you guys read it because I want to make sure this class stays on track. But basically, this is going to be our clever way to do preconditioned conjugate gradients so long as P is positive and semi-definite, even though this product is not the same, because notice that we actually applied it, number one, to a symmetric system of equations. Sneaky, huh? So with that, I'll let you read about it at home, as well as some pointers to some nice preconditioners and other iterative methods. So with that, I will see you guys on Monday. Have a delightful weekend.